binary search algorithm will need how many comparisons to confirm whether that one element is what I want or not?
One.
We need one comparison, right? Okay, very good. And Can's program, which uses linear search algorithm, will also need one comparison to confirm that that's not the element that we are looking for. Is that making any sense? Okay, both search algorithms need to at least look at that one single element to confirm that yes, this is what we want, or no, this is not what we want. And let's make this a little bit bigger. Unfortunately, I have a 386 computer, which is a whole lot slower than a quad core, Core I type of processor. So we'll do a multiplier here. We'll say, we'll take the number of searches that text program needs, and multiply that by a certain number to come up with a real time, the actual amount of time that I need. You can come up with whatever value or whatever unit you want to use for measuring time. I'll just say that we'll use a unit time. In other words, everything when we measure time, it is relative to what I need on my 386 computer to do one comparison or perform one iteration of the loop. Now, since this is text program needs this much time, text duration. In other words, my program will need 1 unit of time to confirm one way or another whether that's what I want. Can's program is a whole lot faster than mine because he has a super duper processor that can do things a lot faster than mine. So we'll just say that Can's computer will take the number of iterations that is needed, and we can multiply that by this number here, because his computer is a whole lot faster. Is that okay so far? Does everybody understand the numbers, what they mean? Okay, so I don't even bother to specify, are we talking about 1 microsecond, 1 millisecond? No, it doesn't matter. It's just a ratio that matters. All right, so now next we move up. But instead of moving up to 2, we move up to 3. How many iterations do you think my algorithm requires to confirm that an element is not in the array? It will need exactly 2. Okay? Because with one comparison, I can throw away 2 elements. One comparison, I throw away 2, I won't have 1 left. So the second comparison will throw away the only remaining element. So I only need 2 to confirm that an element is not in the array. Can's program will need 3 comparisons, because if the number that we are looking for is larger than the last element in the array, then Can's program, being a linear search algorithm, will have to scan through the entire array to confirm that.
When you talk about Can's duration, is it 10,000? This computer 10,000 times faster than your computer?
Yes.
Yeah.
Yep. Well, for each iteration, it only requires, it is 10,000 times faster. But we are not talking about just for a single comparison. We're talking about one iteration of the loop that we are using. So he's gaining a lot because his algorithm is a lot less. There are fewer comparisons in his algorithm. He doesn't have to compute the floor function either, so that's why we have a big, huge discrepancy here. But in this case, Can's algorithm will need 3 comparisons because he needs to scan through the entire array if the element we're looking for is larger than all the values in the array. But I don't need to re-express my equation. I just need to extend the equation I have so far. Okay? So you're saying, Tack, I don't think you have any chance of keeping your job, right? So we'll try 7 next. Okay, there's a specific reason why we have 1, 3, and 7. Because if I start with 7, with one comparison, I will eliminate 4 possibilities. And then I have only 3 left. But I already know that with 3 elements, I only need 2 comparisons. So that means if I have 7 elements to start with, I only need 3 comparisons to confirm that an element is not in the array. Is that okay? But Can's program will need exactly 7 comparisons, or 7 iterations of the loop. So when you look at the time, there's still no comparison. If you compare 3 to 0.0007, there's no comparison right here. Then we say, okay, let's talk about 15 for exactly 15. Okay, are we okay so far? Am I gaining? Just a little bit, right? So let's go ahead and skip a few powers. Let's go to 255. What do you think is the number of comparisons that I need when the array has 255 elements? 8. Okay. My algorithm will need 8. Can's algorithm will need exactly 255. So when you look at the durations, I'm making some headways here. Right? It will take me 8 units of time, and Can's program will only take 0.0255 units of time.
Is there a formula? How you get 8? Is there a quick formula?
Yes.
There is?
Yep, there is one. Okay. Let me move this up to 65535. There are specific reasons why I pick these numbers. They are powers of 2 minus 1. Okay? 1 is 2 to the power of 1 minus 1. 3 is 2 to the power of 2 minus 1. And 7 is 2 to the power of 3 minus 1. 255 is 2 to the power of 8 minus 1. This one is 2 to the power of 16 minus 1. So I need 16 comparisons in this case. But instead of just typing 16, I will use an equation because I'm lazy. So we'll just say that this is the log of this number divided by the log of 2. Great. Yes. Go ahead and round it. Okay. We'll just change the way numbers are formatted. Now it looks good. And Can's program is easy because it will just take whatever number of the size, or whatever the size of the array is. That's exactly the number of iterations his algorithm needs. The amount of time is completely just proportional to the number of searches. Yeah, we have to do that here. There we go. Hey, tech is not winning, but it seems to be gaining a little bit. Okay. What do you guys want to pick next? 2 to the power of what minus 1? 32? Okay, we can do that. So 2 to the power of 32 minus 1. And the rest is easy. I just take this down. Oh, well, I guess tech is keeping his job after all. Are you guys seeing the interesting part of how this algorithm is gaining? Okay. Why am I gaining? After Ken got fired, we kind of met each other at a grocery store, and Ken was still scratching his head, thinking, "How could I have lost to your, program? Because I'm running mine on a Core I processor, running at 3 gigahertz and whatnot." And you have a little 386 SX machine running at 16 megahertz.
Because the ratio for your steps is smaller than the ratio on his steps. So let's say 8 divided by 4 is going to be 4, while 255 by 15 is going to be bigger than 4. So it's going to take you more time. His ratio is bigger than your ratio.
It's because the way the shape of the curve is structured. Okay, it's because of the shape. Okay, so when you look at it, what is the shape of Can's algorithm? If I plot the amount of time, okay, this is time, and this is the size of the problem, or bar A bar. What does it look like for Can's algorithm? It's a straight line, right? Okay, it's a straight line like this. By changing the processor, Okay, if you switch from a core i5, when you switch from the i5 to i7 with a higher clock speed and more cache memory, this curve, can slant like this. Okay, but it is still a linear curve. It is still a straight line, right? What about my algorithm? It's a log. Okay, it's a log
like
function because when you look at the size and you look at the relationship between the amount of time and the size, the amount of time is the log of the size. So it's proportional to the log of the size. So that means, initially I may really be really bad, but at some point my curve will basically flatten out, and at some point these two will meet. And after this point that we meet, mine will go faster because mine increases very, very slowly as the size of the array increases, whereas Ken's algorithm will take the amount of time it takes is proportional to the size of the array. Are we doing okay so far? Okay. So are you guys convinced that this stuff is actually important?
Yes.
Okay. Because I get to keep my job because I picked the right algorithm. Now, when you are at work, okay, when you're searching for algorithms to do a particular thing, many times you don't have to reinvent the wheel. Okay? In fact, very rarely do you have to come up with your own algorithm to solve a problem at work because most common algorithms are already out there. The question is, do you know how to read those algorithms when you look it up from Wikipedia? Let's go to Wikipedia and take a look at the two search algorithms that we have just looked at and see whether it has any entries to talk about how fast exactly is this algorithm. So we go to, we just look for binary search. I think the first two items will be, Wikipedia is the first. Okay, so when you look up, Wikipedia on the binary search algorithm, it is long. Look at this. It's a very long, piece because, not only does it talk about, what the algorithm looks like, it also kind of gives you a proof that the algorithm is correct and a whole bunch of, other stuff. But what we really want to look at is the average case performance. And we look at this, notation here is a big O, with log n inside it. What it means is the amount of time the algorithm takes is proportional to the log of the size of the array. That's all it's saying. The amount of time it takes to solve the problem is proportional to the log of the size of the problem itself, which dictates not the exact curve, but it dictates the shape of the curve. If you have a faster processor, the curve flattens a little bit. When you have a slower processor, the curve, is expanded, vertically a little bit. But you do not change the shape of the curve because you have a faster or a slower processor. So the next thing we want to do is to look up linear search. Right. Thank you. So we want to take a look at linear search. And when you look up linear search, it has, does it have a time complexity? Nope, does not have a time complexity. Oh, it does. It's just not listed the same way as the other one. The linear search complexity is big O of n. So the big O of n, which is this little notation here, is saying the execution time of the linear search algorithm is proportional to the number of elements in the array.